Welcome to this second part of our video lecture series on PDE 1. The first part was covered in 20 and odd lectures, and similar number of lectures will be delivered in the continuation second part. I am P.S. Datti uh, from former faculty from TIFR Center for Applicable Mathematics, Bangalore. Professor Nandkumaran, my colleague and friend for more than 30 years, and myself are giving this set of video lectures. Like in the first part, we will again focus for most part of these lectures on classical theory of PDEs. However, there are some exceptions. So we include a discussion on Hamilton-Jacobi equation and conservation laws. Both are examples of first order Cauchy linear equations which we dealt with in the first part of the course. And in the first part of the course we also mentioned that in the Cauchy linear equations in general the singularities or discontinuities in the solutions occur, and after some finite time will not be able to obtain solution in the classical sense. That is, we cannot obtain solutions which are differentiable for all time, and that necessitated the inclusion of so-called weak solutions, because these problems are of great practical importance, and the solutions for all time need to be defined even in a discontinuous manner. And that brings us to the formulation of uh, weak solution. So what is meant by weak solution of these two important equations, and those things will be dealt uh, in detail as we move on. There is also an inclusion of some introductory lectures on weak formulation of PDEs, and these are meant to arouse some interest, at least in some of you, which who would like to pursue their higher studies in this area of PDEs. So these modern techniques are inevitable if you want to pursue research in the subject of PDEs, and hopefully those few lectures, introductory lectures on weak formulation will be of some help. Okay. So I begin today a discussion on scalar conservation laws, and in the next few hours you will be listening to this in some detail. Okay, a single conservation law is given by this equation. First order Cauchy linear equation, u sub t plus f of ux equal to 0. So as we go along, we'll put further conditions on this nonlinear function f. For the time being, just a general discussion why it is called a conservation equation, and you just look at this integral minus infinity to infinity uxt dx dx. Okay, so this is a function of t. Okay, so let's differentiate that with respect to t. So everything is formal here, so this integral has to be finite, etc., etc. So suppose this differentiation under the integral sign is allowed, so again you just uh, do that, so you will get integral of ut, and that is uh, there is a minus sign here, minus f of ux. So and this is a derivative, so assuming that at infinity they just vanish. Okay, so that will get 0. So there's this quantity is a constant, so it's conserved in time. Okay, and as you go along we'll uh, give more examples. Okay, so another example is from this gas dynamics. In fact, most of the uh, conserved equations are derived from fluid dynamics. So I will discuss some of these things, but not in detail, so that you can refer to any introductory book on fluid dynamics. So there are three equations mainly. So conservation of mass, momentum, and energy. Okay, with other assumptions on the fluid in question. Okay, with some simplification. So if the density of the fluid is a constant, then the momentum equations reduce to this vector equation. So there are three equations here, and this, if you consider just one dimension, so that becomes Burger's equation. So this we have studied even in the first part in great detail, and this was the original idea of Burger's, to take a simplified model in order to study the turbulence nature of the fluid dynamics. Okay, and since then this equation has played an important role in the development of this theory of conservation laws. This is a single equation. Okay, there, whereas if you look at the uh, Euler equations, they are systems. Okay, so system and single equation, there is lots of difference. In fact, many things are still not complete uh, as far as the system of conservation laws are concerned. And this has remained, along with the Hamilton-Jacobi equation, uh, an active research area for many years, and it continues to be one. Okay. Okay. So most of the uh, discussion on this conservation laws is confined to this initial value problem. Okay, so ut plus f of ux equal to 0, and some initial condition is given. Okay, so as you go along, we'll precisely tell you the assumptions on the nonlinearity f and also on the initial condition. Okay, and as we have observed through the example of Burger's equation, and with many initial, very nice smooth initial conditions, we have already seen that the differentiable solutions will not exist for all time. So this t is time variable. Okay, so there is need of considering non-differentiable uh, functions as solutions of this equation. Okay, so let's start with a discussion on what is meant by a weak solution. Okay, that's concept of weak solution. So this is the motivation. So suppose we have a smooth solution, that is a differentiable solution to this problem 1. Okay, and now you multiply this equation by a smooth function. So this CC1, that subscript C denotes compact support. Okay, so this phi as a function of two variables x and t, it has support uh, in this set, such a set. Of course, this set depends on phi. Okay, so as you change this phi, this support also changes, but the structure is the same. Okay, and so this, what does that mean? Again, recall. Okay, so phi of xt will be 0. So for the time being, just call this set as some k. Okay, if xt does not belong to. Okay, so that is meant by the support. So yes, support of phi. Okay, so you take any such function and these are called test functions. So multiply the equation by this phi and integrate. Okay, so since this is 0, so I start with left hand side 0, and where you are integrating with respect to t from 0 to infinity. See, remember, we are interested only in t from 0 to infinity. So with respect to t, it's 0 to infinity, and with respect to x, whole of real line. And now you integrate by parts. Okay, so with respect to t here, I do. Okay, so this minus sign after integration by parts. Okay, and that will produce, since this is a finite uh, quantity there, namely 0, so that will with respect to t variable, it will produce a boundary term. Okay, and that you again integrate with respect to x, so that is phi of x0 u of x0 dx. And with respect to x variable, so this just f phi of x, f of u dx dt, and there are no boundary terms here because of this region. Okay, this phi vanishes outside a finite interval, so there will be no boundary terms here. So there is only boundary term here. Okay, that will also be 0 if phi x0 is 0. Okay, but in general that phi of x0 is not 0 by our this nature of phi we have taken. Okay, and for brevity, let's write this double integral t positive, this one 0 to infinity minus infinity infinity, and t equal to 0, it is simply this integration with respect to x, and we are putting t equal to 0 there. Okay, so this will be just double integral t equal to 0. Okay, and here is the definition. Okay, so u is called a weak solution or generalized solution of the initial value problem. Okay, again just remember that will be the IVP will be dealing with throughout this series of lectures on conservation laws. So if u is a bounded function, so this u L infinity r cross 0 infinity, and this integral relation is satisfied, and that integral relation is precisely this one. So 0 is equal to minus minus minus, so you just make that plus. So u of phi t fu phi x dx dt plus u0x, and that is coming from the initial condition u0x phi x0 dx for all phi which are test functions. Okay, so a test function means it has compact support, and its support is in such a rectangle in the xt plane. Okay, and that's one remark here. Okay, so both in the study of Hamilton-Jacobi equation as well as conservation laws, we will be using some Lebesgue integration theory and Lebesgue theory in general, okay, which we are not theory of measure and integration. Okay, so some arguments crucially depend on this theory, and you better recall from your study of measure and integration some of these arguments. Okay, and this is the only place we are using this modern theory of integration. Otherwise, for most part of the course, we'll be dealing with only smooth functions. Okay, and this is, so this u belongs to L infinity or 0 infinity means u is a measurable function, and it's essentially bounded. Okay, in the Lebesgue theory, you call that essentially bounded except on a set of measure 0. Okay, and that will be sufficient for this integration to make sense, because this integration is only a bounded set of the xt plane. Okay, because this phi has support in a bounded set. Okay, so these integrations, they make sense. And for this definition, you also notice that we do not require any differentiation assumption on the solution u. Okay, it's just a measurable and essentially bounded function. The only requirement on that function is these integrals are finite, and that is taken care of by the boundedness assumption. Okay, so this is the weak formulation of this scalar conservation law. In fact, this is the procedure followed for most of the linear and non-linear PDEs. So you multiply by a test function, suitable test function. So this again class of test functions differ from problem to problem, and you throw all the derivatives on these test functions, okay, by many integration by parts, and you generally end up in the definition of weak solution of a given linear or non-linear PD. Okay. In case the problem is posed in the setting of a Hilbert space, so instead of integration, one uses the elements from the dual space. Okay, that you will see in few introductory lectures on weak formulation. Okay, so this is the definition of this weak solution. So our first task is, suppose u is a weak solution, and suppose it also happens to be a differentiable function. Is it true that it satisfies the equation pointwise? And the answer is yes. In fact, that it should be. Okay, so it's a genuine extension of this definition of weak solution is genuine extension of the classical solution. Okay, so here that small result here. So if u is a weak solution and u is a C1 function, okay, then u is a classical solution. That means, so u also satisfies this pointwise and the initial condition. Okay, so for this, of course, u need not be C1 for all time. So whatever, till whatever time it has that differentiable nature, and that will do. So for that we have to just restrict the support of phi. Okay, so and suppose u is a weak solution and u is C1, though we'll prove that ut plus fux is 0 and ux0 equal to u0x. So by definition we have this u of phi t plus fu phi x dx dt plus integral u0x phi x0 equal to 0 for all test functions phi. So first we consider the test functions phi which have support in AB cross 0t. Okay, that means at phi of x 0, so this means, okay, so this implies phi of x 0 is 0 for all x. Okay, so here I have just written that second integral is absent. Okay, so we have to deal only with the first integral, and that one you integrate by parts again. That we can do because we are assuming u is C1. Okay, and again that's just integration of parts, and again there are no boundary conditions because we have taken the support of phi in such a rectangle. Okay, and so this ut f of ux into phi dx dt equal to 0, and that implies ut f of ux equal to 0, and this is a non-trivial result again from uh, the theory of, okay, so this uh, so integral f phi 0 for all phi test function. So this is a non-trivial result. Okay, so this actually one show that f equal to 0 almost everywhere. Okay, 0 except on a set of measure 0, but in this case, so this is a continuous function. A continuous function which is 0 almost everywhere has to be 0 everywhere. Okay, so this has resemblance to uh, this simple result in analysis. Okay, so if f is a continuous function on 0 1 and 0 to 1, fx x to the n dx equal to 0 for n equal to 0 1 2 etc. So these are called moments of f. So if all the moments of f are 0 and f is a continuous function, then f is identically equal. So very similar to that result, and this result follows from the Weierstrass theorem, namely any continuous function is approximated by a polynomial. Okay, so in other words, the polynomials are dense in this space. So similarly, these test functions are dense in many integrable class of functions, and that gives you this result. Okay, so for this implication is not trivial. Okay, so that we have to again consult your integration theory. Okay, that will be really repeatedly using. Okay, so that's the first part. Okay, so if u is a weak solution and u is a C1 function, okay, then it satisfies the given differential equation, namely ut plus fux equal to 0 pointwise. So what about the initial condition? That's also now easily follows. Okay, and now you take any phi test function. Okay, again you integrate by parts. Okay, and now we get a boundary term here. Okay, so when you integrate by part in this, the first integral, now we get a boundary term, namely ux0 pi x0 dx, and this way already shown to be 0, so that implies this integral t equal to 0 ux0 minus u0 x phi x0 pi x0. Okay, and again the same argument here. Okay, so this is true for all phi, and that implies ux0 equal to 0. Okay, so this so at least one verification that if u is a weak solution and also a C1 function, then u is a classical solution. Okay, so for most of the remaining lectures we'll see several examples and we prove this theorem. Let me just state that. Okay, suppose f is a C2 function, so the now assumptions on the nonlinear function. Okay, f double prime is bigger than 0 and the initial condition is a bounded function, just a bounded function. Okay, then there exists a weak solution. And there, this weak solution in addition enjoys many important properties that we'll discuss one by one, and one such property also implies uh, uniqueness of the solution. So it's not clear that whether the weak solutions are unique or not. So we'll consider some examples, and our approach is of proving this theorem. So this is an important theorem and there are many different ways of proving this theorem, and our approach is so prove using Hamilton-Jacobi equation, and namely we use this Laplace formula for the solution of the Hamilton-Jacobi equation and then derive the so-called Lax-Volinic formula. And we verify, so this will take us some time in deriving this Lax-Volinic formula using the Lax formula, and then we verify the solution given by Lax-Volinic formula is indeed a weak solution of the scalar conservation law. So this will take up in the subsequent classes. Thank you.